an autonomous system and advanced manufacturing and remanufacturing technology. He has published over 600 technical papers and books and has graduated more than 100 PhD students. He is a recipient of several awards, including 5 prizes from the Institution of Mechanical Engineers, a Lifetime Achievement Award from the World Automation Congress, and a Distinguished International Academic Contribution Award from the IEEE. He is a fellow of Royal Academy of Engineering, the Learned Society of Wales, the Society of Manufacturing Engineers, the Institution of Engineering and Technology, and the Institution of Mechanical Engineers. He is the founding editor of the Springer series in advanced manufacturing, the founding editor-in-chief of Cogent Engineering, and the editor-in-chief of International Journal on Interactive Design and Manufacturing. Today's topic he would be talking and teaching us is robotics, disassembly, research, and the dawn of smart remanufacturing. Thank you, Professor Pham. The platform is yours now.
Thank you very much, Professor Chetan, for your kind introduction. Good morning, Professor Chetan. Good afternoon, everybody. As Professor Chetan said, I am from the University of Birmingham. I would like to start by thanking Professor Singh for his kind invitation. It is an honor to present our work at this conference. If I may, I would like to turn off the video so that I can save a bit of bandwidth. And at the end, after my presentation, I will turn on the video if I remember it. And if I don't, please, Professor Chetan, remind me.
Sure. I just wanted to say to the audience, if you have any question, you can hold on at the end of the session, or if you want to put that in the chat, then I will read the questions at the end of the session. Thank you.
Thank you very much. So I also would like to start by thanking the people who have been supporting our project, starting with the industrial partners who are listed here. They have been very helpful with our project, and also our academic partners in China and in Spain, with whom we have done a lot of work, and some of the work will be described here. And then our team members whose work I'm describing today. The presentation is very simple. It's divided into 3 parts. The main part is the middle one. The first part is only to introduce what we mean by remanufacturing for those of you who are not in the area, and also what we mean by smart remanufacturing. Then I will describe robotic disassembly and our research in this area, which is part of the AutoReman project. Auto is autonomous, Reman is remanufacturing. So that's the end goal of the project, is to achieve autonomous remanufacturing. Then a very quick conclusion to the presentation. So what is remanufacturing? There are many definitions, but we follow the standard definition, which is from British Standard, and it is defined as the process of returning a product to at least its original performance with a warranty that is equivalent to or better than that of the newly manufactured product. So I have underlined the keywords there: warranty that is equivalent to or better than the newly manufactured product. Now, there are similar definitions. So the US standard says it's quite a long definition, so I highlighted just the keywords here: like new or better than new. So the remanufactured product should be like a new product or even better than the new product. And I will explain to you how a remanufactured product could be better than the original product. So we are all familiar with manufacturing, which is the process of converting raw materials into the product that we use and then we dispose of. So at the end of the product's life, we throw it away. That is conventional manufacturing. Remanufacturing is part of a circular economy where the used product is returned to its original condition or better than original condition, as I mentioned before. There are other loops in the circular economy, but remanufacturing is one of the loops, and it is an inner loop. So we are familiar with recycling, which is the outermost, and it returns the used product to raw materials. Remanufacturing returns the used product to a new product. So it becomes a new product at the end. And then we have refurbishing, we have reuse and repair. Now, looking at the various Re's, repair gives you a warranty, which is okay, but not as good as other Re. And it does not require so much work than other Re. Renovating, refurbishing requires a bit more work, or sometimes quite a lot more work, and gives you a longer warranty. Reconditioning, further work and longer warranty. Remanufacturing gives the original warranty, or even better than original warranty, but it requires a lot of work. So this is how remanufacturing is positioned relative to the other Re processes. So here are some examples of products before and after remanufacture. So this is part of a generator, and before remanufacture it looks old and disused, and then after remanufacture it looks brand new. The same with this flow meter before remanufacture, after this turbocharger before, after, these brake calipers before and after, this alternator before and after. You can see that externally the products look as new, and internally they also behave like new. Now, why do we want to remanufacture? Now, most of you are material scientists and engineers. You know about the scarcity of materials. Certainly, quite a few materials are very scarce. And it is very important that we don't waste them, that we are able to reuse them. So remanufacture saves a lot of material. So in the case of this turbocharger, remanufacturing saves 98% of material. Saves 98% of materials. You can use 98% of the materials from a turbocharger to produce a remanufactured turbocharger. In the case of this motor, then save 88% of materials. Also, in manufacturing and remanufacturing, you use energy and you produce CO2. In the case of remanufacturing, you save 37% of CO2 emissions. In the case of this motor, 52%. And there are other cases where these numbers differ, but they are still very impressive. So this is another case from Caterpillar, our collaborator, and you can see that greenhouse gas emissions reduced by 62%, water consumption by 93%, and so on. So very impressive savings. Savings in landfill is something that I have not yet mentioned, because you are not throwing things away. You don't need space for landfill. So saving of 99% in the case of this cylinder head. But at the end of the day, for manufacturers, it's the bottom line that is critical. So for a manufacturer, remanufacturing makes a lot of sense, because as you can see here, if you produce a particular widget and it costs £1,000 or $1,000, out of which $660 is in input, so raw materials and energy. $180 are to do with labor. Then you make $160 in profit. The same product, when remanufactured, only requires $198 in raw materials and energy, but it requires quite a lot of manpower, for labor. As I mentioned before, quite a lot of labor is involved. Yet you can sell it at 20% less than the cost of a brand new product and still make 50% more profit than when you manufacture a new product. So for a manufacturer, it makes a lot of sense. You make more profit. For a user, it makes a lot of sense. You save money, 20%. So everybody wins. The environment wins because we don't emit so much carbon dioxide, greenhouse gases. We don't waste resources. Manufacturers win, as you can see. They make a lot of profit, a lot more profit, and users also win. Consumers also win. So it is win-win-win. Now, this is a straightforward sale situation. If the product is leased, the manufacturer makes even more profit, as you can see here. So we see that remanufacturing has environmental, sustainability, and economic benefits. Remanufacturing also has some challenges. The key challenge is uncertainties, and I will explain to you what they mean. So uncertainties in remanufacturing are to do with supply uncertainties. You don't know what quality of the product that you get when you start remanufacturing. So a used product can be quite good or can be very, very poor. So there is quality uncertainty there to the input of the remanufacturing process. The quantities, you don't know how many will be available and when. The quantity and timing are uncertain. Because of those uncertainties, there are operational uncertainties. So you don't know what processing is required for a used product. Some will require a lot of processing, some will require much less processing. Therefore, also the time involved in remanufacturing a product is uncertain. There are demand uncertainties. At the moment, people are not yet familiar with remanufactured products. They still have queries about the quality of the products. By that, I mean users, consumers. So we cannot guess the demand for remanufactured products. So there are many uncertainties there. This information I took from this nice paper published a few years ago. And in order to overcome these uncertainties, you use sensors. People use sensors, they use smart sensors. They are embedded in products. They are used in production systems in order to reduce the amount of uncertainties that come with remanufacturing of used products. Using sensors during the operation of the product, you can monitor the operation of the product. And then by monitoring the condition of the product, you can guess how much life remains in the product, and therefore you can estimate when the product will be available for remanufacture. So you reduce these uncertainties in supply. And you also can record how the product has been used. Because of that, you know what has worn out, what is likely to require which operations. So to reduce all those uncertainties, you also feed back this information to designers of the product to improve the next generation of product. So there are many things you can do in order to improve remanufacturing and also manufacturing. Now, these are some of the Industry 4 technologies, and they have many uses in helping to reduce uncertainties, in helping to make remanufacturing smarter. So by smart remanufacturing, I mean the use of Industry 4.0 technologies, the use of digital technologies to reduce uncertainties in the remanufacturing of process of products. So what is remanufacturing in more detail? We start with the end-of-life product here, then the product has to be disassembled. So this is the first operation in any remanufacturing operation. The first operation is disassembly. The disassembled product is then cleaned. So put through some cleaning machines, some cleaning processes. The cleaned components are inspected, and those that are good are immediately used. Those that are worn out, they can either be repaired or they may need to be replaced. And then the products are reassembled, tested, and then you have your remanufactured product. Now, at this point, I can explain to you how the remanufactured product can be better than the original product. And this is at this point. At this point, when you inspect the product, when you start to use the components, then you can find a new generation of component, and you can replace the old components with a new generation component that might be made of a lighter material, might be made of a stronger material. So in the end, the reassembled product can be better than the original one because it will have some new generation components in it. If you have an electronic product, you might have some new chips in there, some new generation chips, so some new CPU chips. That will be of a new generation and therefore may be faster, may be more accurate, and so on, may last longer. So the remanufactured product can therefore be even better than the original product. At this point, I normally ask the audience, if I see them, to guess the meanings of these two videos. But because I don't see you, I'm going to give the answer to you. So on the left-hand side, you can notice a lot of people are involved in disassembling this engine. On the right-hand side, you can see the dexterity of the person. So disassembly is not an easy process. It is very labor-intensive. And our work in the AutoReman project is to study the fundamental processes of disassembly, to understand them, and to try and develop systems involving robots and automation in order to perform robotic disassembly, to reduce the amount of labor that is needed, and not to replace everybody, but to replace people where it makes sense to replace them. There are some tasks that are dangerous. You will see later on, I will mention some tasks that are dangerous and people need to be removed from there. Some tasks that are heavy, boring, and so on. And it is also good to remove people and let them do more interesting work. So our project is devoted to trying to get fundamental understanding of disassembly processes so that we can devise machines, strategies to perform disassembly in an automatic manner or semi-autonomous manner. I will explain that in a few minutes. Now, we are not the first people to study disassembly. People have studied disassembly for 20, 30 years, but we are, I believe, the first people to focus on the fundamental processes of disassembly to try and derive a deep understanding of disassembly and then to devise systems and machines to perform disassembly autonomously. Now, the project, the AutoReman project, is a 5-year project started in 2016. So the end of the product was a year or two ago, but we are still continuing, the team is still working. The funding from the government has finished, but the team is still running and we are obtaining new funds to continue the project. we have 5 work packages in the AutoReman project. And the first one is to do with disassembly science. So that is very important to us. We study fundamental processes, basic processes, like pulling a pin from a hole, like unscrewing, and so on, to try and understand what is involved there. What are the mechanics of those processes? What are the informatics of the processes? So what information we can gain from measuring the operation. I will explain some sensor work that we have been working on a bit later on. So if we understand the processes, we can design strategies to perform them well, so that the robots don't get into trouble when they perform the operations. If we want eventually to have a system that can work autonomously, then we need to allow the system to be able to plan its operations. So we look at planning of disassembly operations as a big piece of work of ours. And nothing goes to plan with remanufacturing because of all those uncertainties that I mentioned to you. So the ability to replan when something wrong happens is important. And therefore, we look at planning and replanning. And then there will be cases where a task is either too difficult for a robot to perform, or it doesn't make sense economically for the robot to perform, because you need jigs and fixtures and so on. And humans are much better at handling those processes. Therefore, using humans and robots together is important. And we study human-robot collaborative disassembly. And then the final work package is to do with demonstrations. So we demonstrate our work in practical case studies. So we've done so far 3 case studies, and I'll mention one of them. I'll show you one of them in a short video. Before we started our project, we analyzed hundreds of products. In this case, at this point, we have analyzed 438 products. In total, they involved 12,000 operations in order to identify the most common operations. So we found that the most common operations was unscrewing. And then we have separation, which is, you know, as the name implies, pulling things apart, but pulling them in directions that are not homogeneous. We have identified one class of operation, which is pulling in one direction. And we have studied this class and also unscrewing in detail. Separation has too many different operations, and so we have not focused on separation. So we have focused on unscrewing and pulling operations. Unscrewing. Now we have devised systems to look at the vibrations, the use of vibrations to enable objects to become undone, for the screws to be unfastened autonomously, so that we don't have to use a screwdriver or a machine to do the unscrewing. By shaking the objects, we can remove the screws. So here is the rig, and we'll show you a rig that we have designed, and we have used this rig to study how vibrations can cause unscrewing. So we have some results. They take a bit of time to come. Yeah. So this is the rig being used, and we have an object that has 4 screws, and by vibrating the object, we can get the screws to be undone. So you see that this is the tension force in the screws, and the tension reduces to 0 after a bit of shaking. So in this case, about 3 seconds 10 seconds of shaking, then the screws become undone or become loose, and it's very easy then to undo the screws completely. So we have the rig, and we have the simulation results and also experimental results. The experimental results follow the trend of the simulation results. We have built a device to be mounted at the end of the robot arm, and with this device we perform the shaking, and the device is being tested. We haven't got the results to show you yet, but here's the device mounted on the robot. And one of the uses of the device is not only for unscrewing. The device can be used to impact on an object that is stuck during disassembly. So we want to dislodge this object which is stuck, and we have done simulation to show that by performing impacting operations, we can perform the unlodging, the unwedging operation with minimum force on the object. So that's the key. We want to preserve the objects that we disassemble. We don't want to destroy the objects because we want to reuse them as far as possible. Or if we don't damage them so much, then the repair operation will be easier, will be faster. Pulling. We simulate the pulling of a pin from a hole, and we study the forces involved. So we have force sensor, because when you have small tolerances, you cannot use vision. Vision is not very helpful, but you use the tactile sense, the force that you sense. And the force can be used to guide the robot in pulling a pin from a hole without wedging the pin into the hole. Now, when I did my PhD many years ago, I looked at the putting of a pin into a hole. Now, I look at how to pull the pin out of the hole. So many years later, we are learning how to pull the pin out of the hole. So in this case, we have the robot equipped with a force sensor to enable it to sense a force and perform a trajectory that avoids wedging of the pin into the hole. Here we show an exaggerated clearance. So you see quite a lot of clearance, but in practice, the clearance is very small. And wedging can happen if the pin is pulled in the wrong direction. So using force sensing, we are able to avoid wedging the pin into the hole. Now, here is another system which has no force sensing at all. The sensing is done passively. We have springs in the system, and some of you may recognize this as the Stewart platform system, and it has 6 degrees of freedom. It can move up and down, sideways and backward and forwards, and it can rotate about 3 axes. So it enables us to use a robot to pull the pin out of the hole without any sensors. So you can see here a 2D version of it, and the pulling out of the hole can happen without any wedging. And this is the device. Actually, the device was for performing the insertion of the pin into the hole. And this was the device that I designed for my PhD. But now my students are working on this to perform disassembly. And here's a new version of the device, which is actually only a block of rubber with elastic pins, and that enables this shaft to be pulled out of the hole in a compliant fashion, in a passive compliant fashion, like the device that I showed you earlier. But this is more compact and cheaper to build. If your object is flexible enough, when you pull it out, you can wriggle it, like in the case here. And this wriggling enables the robot to pull the pin out of the hole and without excessive force on the pin. So what you see, the robot is moving sideways, doing a bit of wriggling in order to reduce the pulling force. On the left-hand side, the robot just pulls out the pin, and it needs a lot of force to pull the pin. But on the right-hand side, it needs less force by wriggling the pin. So this is another strategy. I think we all have come across it. When we pull something out and it doesn't go out straight, then we wriggle it and we can move it out. So we studied this in theory, and we've done simulation, and here's the practical implementation. We don't just study pulling pin from holes. Here we slide something. So this is another operation, sliding. You notice the robot on the left-hand side started before the robot on the right-hand side, but the robot on the right-hand side finished first. And the secret here is that the robot on the right-hand side does a bit of vibration, very small amplitude vibration, and this again helps. So vibration, wriggling, they all help in the case of disassembly. Finally, the robot on the right-hand side succeeds, although it started quite a lot earlier. We have also enabled robots to learn disassembly operations. So here is learning using a strategy known as reinforcement learning. So with reinforcement learning, the robot learns to maximize a reward. So it finds that at first it doesn't succeed, and by going in a certain direction, the reward increases. So it continues to go in that direction, and finally it will succeed to move the pin along here without being told how to do it. The robot was able to do it. So after a number of episodes of learning, I mentioned planning. So here is an example of planning. We have a water pump made up of 7 parts. It can be disassembled in different ways. This is one way of removing of disassembling the pump, and it requires a number of steps. And this is a second way of doing it. It requires a number of steps. And then the third way of disassembling the pump is this one, and it also requires a number of steps. And the number of steps in the third case is shorter than the number of steps in the first 2 cases. Now, this is a simple pump, so you save a simple product, you save 1 step. In a large product with many components, if you have a good plan, you can save many steps, and therefore you can save time. So this is why people want to do optimal planning of disassembly. Now I'm going to spend hours, I can spend hours talking about disassembly planning, but we don't have time. So if you are interested, there are books that we have written on the topic of disassembly planning. There's a whole book on disassembly planning for remanufacturing here. And there is a book on using the B's algorithm, which is something that we developed in our team, which is an optimization method to perform planning or to perform any optimization problems, to solve any optimization problems. If you are interested, the books are available now, and please have a look at them to find out more about our work on disassembly planning and optimization. As you might remember, one of our work packages is to do with human-robot collaboration. In this case, our focus has been on applying techniques for using humans and robots together. So we focus on demonstrating those techniques. And why we want to do it? We want to do it because of these problems, or of these points. Sometimes jobs are too difficult for humans to do. Then we use robots. Let's say jobs that are heavy or dangerous. Sometimes they are difficult for robots to do. we use humans to do the work, and so on. We do this in order to achieve economic advantages, because for low volume and high variety, then humans are certainly much better than robots. And sometimes you need special jigs and fixtures. And again, it's much better to use humans because jigs and fixtures cost money. Then social motivation, you want to remove people from hot, dusty environments, noisy environments, and so on. Now, we have some demonstrations. The first demonstration that we have done is the disassembly of the water pump that I mentioned earlier. So we have a human and two robots and a press. And the press is a manual one. We just want to illustrate how we can combine people and robots together. So this is an artificial situation. In practice, you probably won't use a human to operate a press. You will use a mechanized press. But here we just want to see, to show that robots can help people. So you can see here, the robot picks up a part, takes it to the press, the person operates the press, and the robot acts like the third hand of the person. It catches the part as it comes out of the press so that the part doesn't fall down. If it falls down, it can bend or it can break. So in this case, the robot uses its force sensor, it grabs the part, and it follows the part as it is being pushed out of the female component. Yeah, so the part is grabbed properly and it is put down properly. So this is possible using a collaborative robot that can follow the action of the person in a compliant manner. It grabs the object and it follows the movement of the object. We did not program the following. The following is done by the robot sensing the force. So this is the capacity of the robot itself. Then we have a second demonstration. This is where we use two robots and a person again to perform the disassembly of a turbocharger. And you can see here the person operating or performing manual job and the robot performing unscrewing also. So person doing unscrewing, but because of the access, it's difficult for the robot to get into a tight space. So the person gets there and does the operation. So I have the whole video to show you. It takes only a few minutes. And hope you will see what we mean. So that's the turbocharger. So this robot goes in and does the unscrewing. You can see the unscrewing operation. Now, because the head of the screw is, the position of it is precisely known to the robot, it has to search for the head. You will see in a minute the search operation performed by the robot. You can see here, it's searching for the head. And it uses its force sensor to do the search operation. Yeah, the search operation is clearer here. Right, it's found it now. Now the person comes in to help. More unscrewing. Now the person has to come in and help because this is not easy. Robot do this operation. Oops, I wanted to move. Yeah. So this is now our third demonstration. In this case, humans are not wanted here because the task is very dangerous. It is a disassembly of a battery, of a car battery. So this is a hybrid car battery. It is not too big, but it's still very dangerous. So we use 4 robots. In this case, there are no humans involved. And we've built a system. The demonstration is too long to show. I will show only bits of it. So for our work, we also look at digital twins. And we have a digital twin of an operation here, showing the robot and the twin performing the movement of the cover of the battery. And this is clearer. You will see the twin and the robot performing a particular operation. And just to show you that it is a real twin, we will see later on a person moving the robot and the twin following the movement. After this, you will see that demonstration. Yes, the person moves the robot, and the twin follows the movement. So it's a real twin now. Here's another bit of the operation. The robot using its vision sensor. So here now we use vision sensor to locate a cable, and then it comes and picks up the cable. It pulls it out. But the cable is stuck. So it has to find a way to remove it. Looks for the cable again. We have not optimized the system for speed. We just want to show that things can be done. So you focus on the movement now. Wriggling happens here in order to remove the cable. So the robot is able to sense what the cable is off using its vision and force sensor. In conclusion, remanufacturing, we have seen, is good for the economy and the planet. Disassembly is the first step in remanufacturing, and it is very labor intensive. Our project, our AutoReman project, is focused on developing an understanding of disassembly to help us design systems to perform robotic disassembly and enabling smart remanufacturing. There are many research problems remaining. I've listed a number of them here. These problems can take people years to solve. That is why we are only at the dawn of autonomous remanufacture, at the dawn of smart remanufacturing. There's a lot of work to do. Just to illustrate for you, the pack and hold problem that I studied many years ago has now become a topic in Science Direct. It's a Science Direct topic with many people publishing in this area. The problems was investigated first in the 1960s, and even in 2023, people are still writing about this pack and hold problem. We wrote our first paper on pack out of hold problem, disassembly, 2 or 3 years ago. I'm sure in 10, 20 years time, people will still study that problem. There are many things for us to do in this area. So as the EU Commissioner for the Environment said, with the circular economy, we are looking at a triple win. I mentioned the triple win before. Society can win, businesses can win, and the environment can win. It's a major opportunity, and we need to make sure that we grasp it. And we can't do it on our own. We need help. And you are very welcome to join us to work on this topic of autonomous remanufacturing and robotic disassembly. Thank you.